G'day viewers. In this segment we'll talk about the linked state approach to routing. So our topic is really computing the shortest path that we've talked about previously in a distributed setting that corresponds to a network. We've looked at distance vector routing. Now we'll look at linked state, a very different approach. One in which there are a couple of phases. First everyone floods the information and then we compute the routes. So it's interesting to compare linked state routing with the distance vector approach that we've seen, because they operate quite differently. The distance vector approach spread the work of computing the routes out across all of the nodes of the network. In linked state, we give everyone a copy of the topology and let everyone compute their own routes. So we're really replicating a lot of work in some ways, as opposed to having everyone work cooperatively as in distance vector. So linked state is actually a little closer to that old view of giving everyone a map of the network and then letting them work out their own routes. Now, linked state routing is widely used in practice. It's been around for a long time, almost as long as distance vector. It's been used in the ARPANET since about, what's it say here, 1979 onwards. And many modern networks today use protocols that are based on the linked state approach. Here I mentioned OSPF and ISIS, which we'll just mention very briefly at the end. But these are protocols that would be used in ISP networks, large enterprise networks like on campus or in a big company. They all use this linked state approach. Before I dive into the details of the linked state approach, let me just remind you of the setting we're working in. This is the same as the setting for distance vector. It's really our distributed setting, which makes routing more complicated than simply looking at a picture and being able to centrally compute things. I'll remind you briefly. So, in this setting, the nodes only know about who they're connected to, their neighbors and their cost to the neighbors. They don't a priori, when they're turned on, know the whole topology. They can only talk to their neighbors using messages to find out what's going on for the network at large. So they have no other way to gain information about the network. All of the nodes are running the same algorithm concurrently. None of the nodes are special, so there's no centralized controller. They're just going to have to agree amongst themselves on what's going on. And they operate in parallel, so they'll have to coordinate their actions. And finally, since this is routing, we would like to be able to deal with failed components. So some of the nodes and links may fail, and we would like the remaining portion of the network that's working to correctly find routes. Messages may also be lost. So that's the setting. What about the linked state algorithm? Here's how it works. There are two phases. In the first phase, each node floods information about its local portion of the topology to everyone else using what's called linked state packets. In this way, every node will get a picture of the full topology. So we do this whenever the topology changes or when we start. And then, when everyone has the full topology, we'll move from step 1 to step 2. Each node is simply going to compute its own routes and forwarding table. So as you can see, the first step here uses flooding, which we've looked at previously, and the second step uses Dijkstra's algorithm, which we've also looked at previously. Linked state really just combines these two steps, and that's how it works. I'll go into just a little more detail. So the first phase, this flooding to disseminate the topology. Each node is going to flood what is called a linked state packet that describes their portion of the topology. So I've shown the linked state packet for node E here. And you can see from node E, if I just look at node E, its portion of the topology includes a link to D. Actually, let me go through it in order. It includes a link to A, which I'm drawing over here, with cost 10, then a link to B with cost 4, and you can see in the linked state packet it lists all of the connectivity from node E, so we can see there's a link here to A at cost 10, B at cost 4, and similarly there's C here, D, trace over, and then E, well, there's no connection to E because that's where we are, and there is a connection to F. All of those are listed in this vector with the appropriate cost. That is the linked state packet. That's what node E will flood out. And every other node will do similarly for its portion of the topology. Well, once that phase 1 is completed, every node will have received every other node's linked state packet. By putting them together, they'll have a picture of the complete topology. Phase 2 is to compute the routes. All we do is have every node run Dijkstra's algorithm. So there's some replicated computation here. The nodes are looking for the source trees from themselves out, and so that can be different in different parts of the topology, although there's definitely some overlap here. Once we find the source tree at a node, we'll be able to compile the forwarding table from it directly. It sort of tells us all we need to know, and that's it. Let's look in just a little more detail to get comfortable with that. Here at node E, again, I've shown the source tree that is the result of running Dijkstra's algorithm. So node E will gain this picture and gain this source tree by itself by going through these steps. And it will then know which way to go to reach all of the nodes. What I've done now from this source tree, all of the different lines here have arrows which show the path to take. For instance, to get from E to A, I follow this path through the network, through here and over here, through E, C, B, A. What I can do now is simply compile it into a forwarding table. The forwarding table lists for every destination the next step. So for instance, to get to A, the next step is simply to forward to C. And that's all E needs to know. C will then take care of the packet from then on. And similarly for all of the other destinations. That's our forwarding table. And if that's all that's going on in the network, we're done. But of course, the whole purpose of routing protocols is to be able to adapt to changes. So when there's any change in the topology because a component has failed, or maybe because a new router or link has been added, we want to redo some of this process, go through the phases again. So you'll flood any updated versions of the link state packets and recompute the routes. Let's look at an example here of just what would happen. What is going to happen when there's a failure is that the nodes that are adjacent to the failed link or node will notice that something's changed. They'll be able to send updated information, and everyone who receives it will be able to recompute. So you can see here, I've failed node G. It's gone. Just, I don't know, it blew up. What will happen? Eventually its neighbors B and F should realize that it's gone. They'll need to be exchanging some sort of regular hello message to make sure that it's alive, but eventually when there's no answer, they'll notice that it's gone. At this stage, they can issue updated link state packets. In their link state packets, I've listed the same neighbors as before, but you can see I've changed the cost from both those nodes to reach G to be infinity, meaning this link does not work. The cost is infinite, so don't take it. When that information is spread around, the other nodes will recompute and they'll work out paths which do not go through G. Now, if you think about it, you might notice that there's a subtle difference between a link failure and a node failure. When there is a link failure, then both of the nodes that are adjacent that connect to the link will notice that the link no longer carries packets, so they'll both send updated link state packets saying the cost of that link is infinity. And therefore the link will be removed from the topology effectively when nodes calculate their links. Now imagine though that there's a node failure. This is kind of interesting. Well, all of the neighbors of that node will notice that they can no longer talk to it over the link, so there's something wrong with the link to the node. Actually, these neighbors don't know whether it's their link to the node that's failed or the node that's failed. Both of these cases look the same. In any case, all of the neighbors of the failed node will notice that something's gone wrong, and they'll be able to issue updated link state packets that say they can't reach that node anymore. The node that's failed, however, won't issue a new link state packet. I mean, it's failed. It can hardly send a message saying, hi, I'm sorry I failed, because it's no longer there. And it's very unlikely we could count on it to issue something saying, I'm going to fail. That's just not the way failures work. However, it's okay here. Because since all of the neighbors send messages saying they can no longer get to that node, the shortest path computation will effectively remove paths which go through the node, even though that node didn't send an update itself saying that its links had changed to cost infinity. It's interesting if you think about it. And just for the sake of completeness, let me mention that there are other changes. For instance, you might add new links or nodes to the topology. In this case, The nodes that have the new links or the new nodes will send updated link state packets. Everyone will learn of extra bits of the topology, and they'll use some of those new links and nodes as they recompute the shortest paths. Really here, additions are the easy case. It's failures where someone fails and can no longer tell everyone they fail, which are the tricky case. But we want routing to be able to adapt to either one, of course. Now, to be fair, I also want to tell you that there are complications in link state protocols. I'm making it sound kind of easy, and I'm describing the normal operation, the normal cases. They work as I've described them. But when you design a protocol, you want it to be correct and work pretty much no matter what happens. And there are some bizarre cases that we could come up with. And I've made up some here. Now, as part of flooding, you have a sequence number on the flood so that we can stop the flood and only flood new information. What's going to happen when this sequence number reaches its maximum? We could make that maximum very high, but then what's going to happen if the sequence number somehow gets corrupted to a very high number and gets close to the maximum? This seems very unlikely, but the point is we don't want the network to be jammed up permanently if this happens. Another case would be that a node might crash, and when it comes back up, it's forgotten what sequence number it was using before. It can't just start at 0 again because other nodes might know higher sequence numbers for its messages that are flood, and so they won't listen to the low-numbered sequence messages. Or, other bizarre cases, the network could partition itself. It could divide into two components due to failures. Both of these components could evolve independently, and then when the network connects itself again, each side could think the other portion of the network is in a different state, and we would need to fix that. Wow, this is a little messy. Really, a lot of the complexity of real protocols has to do with handling these corner cases, so that things work well in the common case, but they are correct even in these weird cases. I'm not going to go into these complications in any detail at all. I just want to point out to you that it's important that real protocols handle them. You can read a little bit more about them in your text. I'll tell you one strategy that's used, and that is aging. It's very useful. So one strategy that's used is that we include a timestamp on all of the link state packets and most information that goes around networks. If this information is not refreshed over time because whatever created it has gone away, then we forget the old information. This tends to remove old information which is no longer relevant from our network and lets the network get on and adapt to the real situation that we're now faced with. So this is used in link state protocols, but it's also a generally useful strategy. Okay, what else about link state? One thing we've reached now that we've gone over it, is we can compare it briefly with distance vector. This is useful just to see some of the differences between the two. Here's a table that lists our goals for routing protocols from long ago, and we'll see how the two stack up. Now, for correctness, we wanted to be able to calculate correct paths even in this distributed environment. The two approaches use different algorithms. Link state's based on Dijkstra with some replication. Distance vector is based on a version of the Bellman-Ford algorithm, which has been distributed. Okay, different approaches, but they both work. In terms of efficient and fair paths, we're using our shortest path framework where we assign costs to links for both. It's the same in both. Well, where they differ a little bit is in these last two entries. Convergence. We would like rapid convergence to the new routes after any kind of change to the topology, like a failure. We've seen that distance vector can be slow in some cases. It can have this count to infinity and require many exchanges. Whereas link state generally tends to provide fast convergence. All you have to do is flood the new topology and everyone recomputes, so it wins here. In terms of scalability, however, the trade-off is the other way around. Distance vector really has excellent scalability in terms of storage and computation at a node because it does the minimum. We just have, the list of nodes. The computation is really adding numbers and comparing them. You can't beat it. Link state, on the other hand, has more computation. The amount of computing we need to do and storage to store the whole graph grows superlinearly with the network, so it increases more rapidly than the size of the network. So distance vector actually wins in terms of scalability here. It's an interesting trade-off. Okay, and finally, I'll just mention a couple of real protocols which use the linked state approach. And they are ISIS, Intermediate System to Intermediate System, and OSPF, Open Shortest Path First. OSPF is really the IETF or Internet version of the ISIS protocol, which had its roots more on the OSI side of the house. These are modern linked state protocols. They're very widely used in ISPs and large enterprises. They have supplanted distance vector protocols because they have different, better convergence behavior. Even though they require a little more computation, well, computation's gotten cheaper over time. The basic operation is as I've described it, so you know the heart of how they work with the linked state protocol. I'll also tell you they have many more features that are added. There are notions, for instance, of different kind of regions so that will help to scale the protocol to larger networks, or stub areas so that it's easy to compute routes for stub areas. You just need to, if you're in it, go out. You don't need to worry about doing a lot of shortest path computation. Don't worry too much about these features. There are many of them in any real protocol, and I'm just mentioning them so you have some sense. But you know how these protocols work, and now you have a sense of the linked state approach to routing.